Is that distracting to have like the video?
You know, I think I'll probably not see it. Who knows?
You what?
If it is distracting, I'll let you know.
Okay.
So which board are you just trying to split the difference between the two boards?
I'm trying to get the two. I'm trying to get both. I guess I'm not as close as I want to be. Yeah.
Okay.
Oh, you can't set it up in the middle because there are no.
There are no.
And I think even if you could, it's too what? Okay, so let's recall what we've done so far. So, as a sort of leisurely introduction, we decided that the way we want to think of the TTFT is we have field functors f sub I, so f sub k, from manifolds of dimension k and homeomorphisms into sets. This is for k less than or equal to n. And we have local relations, we just saw the subset of fields on a ball. And we have this for all C, which is a field on the boundary of the ball. And these things have to satisfy some axioms, which might be a little bit complicated, but they're a lot simpler than sort of T-Siegel style axioms. And so, what are they for the local relations? We wanted to imply if we think of it as an equivalence relation on these sort of fields or pictures we're drawing on the ball, we want it to be at least as strong as isotopy. So A and B are in U of A is isotopic to B. And actually, I left something, when I was giving the axioms last time, I sort of changed my mind in the middle of the lecture and decided I didn't want to go into all the fine detail, the fine print. So I owe you the fine print, but I thought it'd be nicer to see examples which force this fine print upon you before just laying it out there. But one thing we want something slightly more, I'm just going to say extended isotopic, so it's something a little bit more we need. And the second thing we needed is that we'll just say it's U is an ideal with respect to moving. So that means if we have something in U and then we glue on something else arbitrary, the result is still U. So these are the things that we're dividing. And then these field functors, I want to write it down, but all we really required of them is that we can restrict to the boundary and things glue together nicely. It's easy to find examples of things like that. You don't have to work too hard. And our favorite examples of things like this are, for the field functors, we can take maps into a space, or we can take some kind of decorated cell complex sitting inside our manifolds, which can be thought of as, if you're given a traditional ring category, it could be the string diagrams, dual to pasting diagrams on that category. Those are a lot of simpler examples that require you to define categories and anything like that. And then the local relations are just isotoping the things coming from, well, I So local relations depend on the example. Okay, so this is the basis. So we want to construct everything that's familiar from TKFTs, starting with just this.
So this gluing thing is some structure on our functors. We assume there's some operation that we're calling multiplying.
Yes, yes. Yeah, so we've got, yeah, it's sort of, it's a map from a fiber product of things in the two pieces into the loop. And some of the fine print is that that map is not necessarily onto, but because things might not be, you can't, if you take some arbitrary field, you can't cut it anywhere, but you can cut it almost anywhere in some sense. So that's what I did make precise last time. But in all the examples we'll consider, it's clear enough how things behave. Okay, so what is it that we want to construct? Let me make this table. So I'm going to consider the invariance for a closed manifold. The invariant for a manifold with boundary. And how we describe gluing manifolds together. And we're going to do this in Gn+1 and -1 all the way down to 0. So we've talked about some of the boxes here. We actually started in this box, and so we have a vector space A of a manifold with some boundary condition. Vector spaces, because we also want to consider the dual space. Z of M star. And then if the manifold had I'm sorry, this is a closed manifold, so I shouldn't be writing the boundary condition there. So these are just vector spaces. If the manifold has the boundary, we could put a boundary condition on there, like we just did, and get another vector space. But it's actually nicer to think of it as an organized collection of vector spaces parameterized by the boundary condition. So we have a set of all A of them with some boundary condition. Similarly, set of dual things. And these things are organized. How are they organized? Well, before I say that, we have to, where we put an n-1, where we have a one category A of there, and we also have a dual thing. So dual will always mean maps from this thing to the trivial object. So for one category, that translates into a representation. I mean, we'll talk about this more later, but our maps between one categories are going to be bimodules. So a bimodule from this category to the trivial category is really just the module for the category representation. Okay, so now we can say what these things are. I'm going to say they're elements of Z of boundary M. What does that mean? Well, boundary M was a representation of this, so it just says that these things are organized into representations of this category. So, talked about that a few different times. And so on. So we're always going to have in the minus k, we're going to have a minus k categories, A and Z, all the way down to 0, where we just have an n category. And then it's always going to be the case that
What is X?
X is just some manifold. Some manifold. Sorry. So I'm just describing what the things we're going to construct out.
So X and M and Y.
Oh, yeah, X and M. I'm sorry, X. It isn't H. It is W. Yeah, sorry. I mean, sometimes I always try to reserve W for n plus 1 manifolds, M for n, Y for n minus 1, but sometimes it's good to use the same letter. Those conventions are hopelessly jumbled up. Okay, but today we want to talk about the top thing. And the top thing's a little bit different. All of these we get sort of canonically. We don't have to chop our manifold in pieces. They're obviously invariants. So from here down, things work out very nicely. But for here, we have to do a little bit of combinatorial work, and that's what I'm going to talk about today. So we said last time that we expected for a closed n plus 1 manifold, we just had a path integral. Call it X. Now I'll call it W. So this is just a complex number. And for in the boundary case, we have Z of W lying in this vector space for its boundary. In other words, Z of W is a map from skein module space to C. Oh, and I didn't mention, so the gluing, what is gluing here? We take tensor product over 1 categories. Next down, the gluing wall with the tensor product over 2 category, and so on. And here is just comparing vector spaces. Tracing line. More explicit. So why did I draw this chart? One, just to sort of help us keep track about where we are in all these discussions. So we've pretty much defined things here and talked a little bit about this. We need to sort of work our way down and show how we get things all the way down to 0. But then using different techniques, we need to talk about the top thing. But also just to say that it's more usual in TQFTs just to start with this. Like this is somehow axiom. So if you ask most people or look at most papers, what's a TQFT? You're likely to get an answer that, well, it's a collection of functors, usually just the Z ones, for manifolds, all these things, and they glue together and bring these various tensor product things. So to make a definition of that, you have to define what you mean by a tensor product over a K category. It's a lot of data, and so the point of doing it this way is our starting data is simpler. And also, we have concrete objects that behave in concrete ways when we glue them together. So instead of having to dream up some definition of ring categories and how they tense together, and the possibility we might get it wrong, we just have to sort of describe how these examples work. Okay, so
maybe you talked about this later, but how do you avoid defining any category?
Because what I do instead is I define these field functors and local relations, and part of the point, this is kind of a disguised version of an in category. So briefly, sitting inside here is the category of balls of dimension K. And so we can think of Fk of a ball as being the K morphisms in some category. And there was a list of axioms we wrote down for field functors, for example. We can glue them together, but that's like composition of K morphisms. We can restrict to the boundary, that's like having a domain in the range. You can take a product with I, that's like identity morphisms. So this is in the blog paper with Scott. That's discussed in some detail. But so we have sort of 3 different notions. We have field things, we have this disk-like in categories, which is just taking this restricting the ball, so you can sort of forgetfully go from there to there, and then we have traditional in categories. And to get from here to here, you can just sort of restrict not just to any old ball, but to the standard ball. You sort of skeletonize things even further. So this is right down. This is restricting the balls. This is restricting the standard ball. So it's relatively easy to go in this direction, and you can actually go the other way. You can take string diagrams and construct something going here, and you can from balls to manifolds or some kind of colon type construction. So with some work, and depending on the details of which traditional in-category definition you're looking at, you can show that these things are equivalent. But of the three, I think this is by far the nicest and easiest. So rather than start with in-categories and construct fields, it's actually easier just to start with. For most of the examples we work with, it's easier to describe it this way than to start. But it's good to know this if you want to make contact with other entities. So I think because of the video, I'm using only these two boards. Okay, so we're talking about n+1 manifolds. So what do we want? So what I'm going to do is say, here are some axioms that we would expect these things to behave, and then state a theorem saying that under certain additional assumptions, you can construct something like that. So I'll call this path integral axioms, and to make my favorite drawing, a manifold. So we'll call this manifold W, it's n+1 dimensional, it's WCGL. The boundary conditions here I'll call C sub GL. The manifold I'm moving along, I'll call it M. So there's one copy of M, here's another copy of M. The boundary conditions on here I'll call just C. And we've got some new boundary here, which I will label in a moment. So this is the situation we want to describe. So we're going to have treat this two axioms. I'll call it the path integral axiom, and there we want to take the path integral of the Gleed manifold. The value. Now we're going to think of the path integral as some kind of function like this. So the Gleed manifold evaluated under the new boundary conditions, and we want to express that in terms of the Coven manifold. And what it is, we just assume we have inner products on the vector space, and we take a trace, but I want to write it in a particular form that's amenable to computation. So this is going to be the sum over something of the path integral of W evaluated on, let's see, the Coyote boundary conditions, but that's not complete. So we've got this new boundary here. We have to substitute something. So I want to sum over E sub I, which is some orthogonal basis of scheme module for n with boundary conditions D. What is D? Restriction of C to this n minus 1 manifold. So once we've got some EI, so the EIs are there, and there, and then we can glue together like that. I should probably put a bar over this because when you flip things, that's another part of the fine print of the definition of fields that I emphasize. And then there's a correction factor. We multiply by 1 over the inner product of the I for the set. So that formula we will use over and over again in the next couple of days. But I expressed this in terms of an inner product on here, which I haven't mentioned yet. So I need to, so part of the package of having a path integral is second axiom, called IP for inner product, and that says that for x and y can the same module, the inner product of x and y is equal, and maybe say is by definition, let's just say equal, to the path integral of m cross I evaluated on x through y. So I characterize the path integral in terms of these inner products, and these inner products are defined in terms of the path integral. So you might think it's kind of circular, but in fact, what we'll see is it's these things are amenable to sort of inductive construction. You can start with the very simplest manifolds, and then by gluing, figure out what the inner products are, and then figure out the path integral of a few more manifolds, and then figure out some more inner products, and eventually you get everything. That's the idea of the proof of the theorem that I'm going to state next. So, I guess maybe I should note that path integral axioms imply a few things. One, they imply that the dimension of A of any n-manifold with any boundary conditions is less than infinity. So we have this finite dimensionality. And well, I think I guess I want to add an additional assumption, which one could imagine loosely, but I want these inner products to be, one might be tempted to say positive definite, but we'll have some examples where they sometimes turn out to be negative definite for depending on the manifold and boundary conditions. So we'll just say it's called positive or negative definite. Yeah, so I'm changing gears here, but maybe I'll just make this part of the definition of what we want, and you can think afterwards about would it make sense to loosen that assumption. Okay, so under the assumption of positive definiteness, another consequence of this is that the one category A of a minus one manifold, some boundary conditions is semi-simple.
What is the IP axiom? Is that an axiom or a definition?
Let's make it an axiom. So we'll say that the data. So these are the conditions. I should have stated what the data is, and the data is. I'll put it back here.
I guess my question was, what do you start with?
Yeah, that's what I was saying. So what you start with is for for all n+1 manifolds, you want z and w lying in the boundary w. In other words, we have these functions like this for all manifolds, and for all in C, inner product. Square brackets. So assume we're given that. And then with the axioms is that they have to be compatible. So in fact, we can compute the inner products in terms of the manifolds. So we could have taken this as a definition, but to make things non-circular, let's assume we're given this. So why does that imply that these things are semi-simple? Well, it's just this usual idea that if you have the right kind of inner product on a algebra, more generally on a one category, you can use it to take orthogonal complements, and that means that any sub-representation has a dual, and that's kind of semi-simple by definition. So what we're going to see is that basically what we want to do is a converse to this. We want to say if we've got if the dimensions turn out to be finite, and if we can find some sort of positive definite inner products, then we can reconstruct the path of the. So let's state that now. Theorem. So fix fields and local relations as above. And let little z be some element of the path integral of, let's call it the boundary of the n+1 law. So this be such that the pairing this is where it's so we want this to be positive definite. This is a definite. C. Assume also that the dimension of the scaling algebra for any n manifold is finite. Then there exists unique path integral. By path integral, I mean not just these things, but also the inner products. And that satisfy those axioms. So this is W. And finally, such that the path integral of the n+1 law is equal to this little z that we started with. Okay, so what is this saying? It's just saying that we've got the fields and relations as before. Suppose someone tells you, hey, I know the path integral of the n+1 law. And then what you have to do is you have to check, one, that your Scaling models are always finite dimensional, which in practice is often easy to check. And then you have to check just on the involve that these pairings we get by basically taking this formula and taking m to be the n-ball and then substituting little z for the path interval. You have to check that these are always definite. And if you do that, then everything else works. And in practice, these are often easy conditions to check. So once you know, going back to something we said earlier, if we were doing real physics, the path interval would be some scary interval with an infinite dimensional space that doesn't have a reason to measure. And we're just saying, well, if we can do it for the simplest possible n+1 manifold, then via combinatorics we can figure everything else out. So we just think of this as some black box. Okay, so the idea of the proof is to just inductively construct it. And what's the induction? Are we indexing the induction? We consider n+1 manifolds, which are just a disjoint union of balls. Then we know how to do it because that's our starting data. And then we'll prove it for n+1 manifolds that have 0 and 1 handles and then 0 and 2 handles and so on. And that will show the uniqueness part, so that this is enough to calculate for anything, but then we have to show that if we had chosen a different handle decomposition, we would have gotten the same answer. Existence. But I want to, rather than doing it in the abstract, I'd like to do it concretely for an n=2 example. So I need to pause a minute to describe that example, or that family of examples. So, and I think, even though we usually go for an hour and a half, but someone else has a room, so I need to stop.
M cross I in the definition of the inner product is again that hinged.
Yes, it is. Yeah. So the picture that goes along with this is x bar on top.
And then x bar dot y is going to live in its boundary.
Yes. Yeah, thanks. I should have.
I see. So that's what's happening here. In the theorem Z of x bar dot y is like
Yeah. So
the top half of the sphere and the bottom half of the sphere.
right, we've got the n+1 ball here, and its boundary we have 2 copies of B sub n. At the bottom, C is the boundary condition along this n-1 sphere. I'm looking for an eraser. I guess I should also point out that the method of proof of this is also going to give us sort of a way of calculating in terms of a handle decomposition, and those are going to turn into these state sum formulas that are kind of at the historical beginnings of the topic. And so, one thing we'll want to do is specialize this theorem to a lot of particular F's and U's and see how we reconstruct this state sum type invariance. So, there's 2 example. Establish some terminology. So, what I'm describing here, more or less, I'm defining what might be called strict typical two category. It might also be called some sort of generalized planar algebra. So what do we need for this? We want some finite set curly L sub 0 of call them region colors. Thinking in terms of planar algebra. I just call them zero morphisms if we're thinking in terms of two categories. We want a set not necessarily finite of set L sub 1 of the planar algebras we call the strand types. For two category, we would call it a generating set of homomorphisms. Generating in the sense of composing one forms or stacking things together. And then, oh, and this L, I think I should put a superscripts. So, that one is actually going to depend in the case, an important special case is when there's only one region color. That's the sort of two-sub category thing, and I might sort of lapse into assuming that from now and then. But in general, if you've got some kind of strand, it's got strand of type A, it's got region colors X and Y on the bottom. So this L sub X for all X and Y objects we want set of these. And we also want on this an involution. It's basically turning things upside down. So A hat, and if we see a strand, my strands are always going to be oriented. And if it's oriented this way with A, that's consider that the same thing as reversing the orientation. In practice, these labels A are often representations of something, and then A has representation. Okay, so for all declarations of the circle with some number of strands on the outside, not going to worry about the region colors for a moment. So for anything like that, we want a vector space. So this example. So just given some collection of data, we have a vector space which also is finite dimensional. And then finally, we want a way of composing these things. So given some, so with the data we have so far, we can draw diagrams of the disk. So given some such diagram, strands, connecting these guys together. So the strands will all be oriented like things in L1, the regions will be labeled by things in L0. We've got elements of these vertices are labeled by elements of the appropriate vector space. By which, in two category language, these vector spaces are just the two morphisms. And planar algebra language, box spaces or something. So given this, we have a map that we just call the evaluation map that take, on the outside we have A, B, C, all the way to say Z, and the evaluation map takes us to V, so in other words, we can take that diagram and replace it with this one big thick under that. So,
So the regions are labeled with colors or objects.
Yeah.
And the edges are labeled with.
so let me give a concrete example. So how does one? So I want to claim, there are many interesting examples of things like this, and the classification problem is interesting. But how do you construct examples? One way to do it, which turns out to be actually a general way, not a very practical way.
Well, I'm not even sure what this is. Like this thing is like this. What do these have to satisfy? Or is there some structure?
Yeah. So I guess I was doing it quickly because I was assuming perhaps incorrectly that people were familiar with things like this, and I didn't want to bore you. Okay. No. Okay. I see these two heads shaking. I know one person is all of that. Okay. You're also.
I don't either.
Okay. So.
The
Okay. So.
majority.
I'm glad you spoke up. So I guess I should go a little. Okay. Well, let me mention the example. So what I was trying to do is describe all at once examples from a few different things. So let me describe the individual examples and we'll see what they have in common. So one that might be familiar. Examples. So we can take L naught to be some collection of piece of i's, maybe it's P and Q. Where each of them is R von Neumann algebras. You prefer is thinking of some finite dimensional algebra, but that's less interesting. So we've got algebras for each pair piece. So we picked out some von Neumann algebras. For each pair P and Q, L naught, we choose some set of PQ bimodules. Not all possible ones, but just some set that we like. And then finally, we'll define V of, I'm going to break the symmetry of the disk to have an upper and lower particle, it won't matter. So P1, P2, P3, P1, P2, P3. This we define to be the intertwiners between P1 tensor, P2 tensor, 3, Okay, so what do these tensors mean? These are bimodules, so I'm actually tensoring over the algebra that comes in between. So this would be some. Oh, I'm sorry. P and Q are the letters I usually use for try again. P1 on the regions, P2, P3, I'm calling regions, and then here I have M, which is a P1, P2 bimodule, and this will be labeled by M prime, which is a P2, P3 bimodule. And then along here, so P4, this is again just P1. And I have a couple of bimodules in, which is P1, P4, P prime, which is P2. So this is the data on the outside of this. Oh,
No, it's okay.
Yeah.
Take your time. We don't explain immediately for one.
oh, okay. So, given all this,
So bimodule means Hilbert space, or the with an action of the one Neumann algebra, or the usual kind?
yeah, I think in this case, you know, I'm not an expert in analyticals, but I think we do want Hilbert spaces where these are active.
And then the tensor product would be something weird like the confusion or something like that?
Yeah.
Okay.
Yeah, so maybe it's, perhaps for purposes of illustration, maybe I should just think finite dimensional algebras where we don't have to worry about that. And I'll mention, in a moment I'll mention why I'm saying Neumann algebra. Anyway, given all this, I need to produce a vector space, and it's just the intertwiners, so it's, so P1, P3, between the two bimodules. So we've got M tensor over P2 and prime, and then go backwards. M tensor over P4 and prime, and just this absolute there. So, okay, I kind of mangled the explanation, but so how many people have never seen like algebras, bimodules, intertwiners, that kind of thing? Okay. Okay. So the point is that those things form a two category language. They form a two category where the objects are algebras, the one morphisms are bimodules, the two morphisms are intertwiners, and importantly for us, this is not just any old two categories, it's a pivotal two category. We can turn things around. We have sort of adjoints that are built in. And all the part of the strategy for what we're doing here, we don't want to define sort of weak categories without adjoints and then give a list of things additional things that need to satisfy those. So we're only considering things that are dualizable or have adjoints from the get-go. Okay, so why did I make my life hard by saying von Neumann algebra here? Well, the point is if you if you add von Neumann algebra, then in some sense this is a completely general example. Anything satisfying those axioms that I sketched up there is isomorphic to something where anything can be embedded in this category. And in fact, there's a talk this afternoon on that subject. So that was originally proved by G&A Jones and Fleet Tinto, and I used a paper with me and Jones, and had a simpler proof. And those papers don't state it in this kind of generality, but if you look at the proof, at least in the second paper, there's nothing to prevent you from adding arbitrarily many region colors and arbitrarily many strand types. So this is
In Vaughn's current planar algebras course, this is sort of how he's defining a planar algebra.
Oh, really?
It's very open on whatever boundary conditions,
Okay.
whatever oriented strands, whatever.
Okay, so I guess I don't need to say generalized. I mean, there was a time when he insisted two colors, anything else is foolish. I guess he's coming around. And another set of examples might be called ref of UQ of G. So what does this mean? G is a Lie algebra. U of G is a universal enveloping algebra. Q is some Q deformation. And we can look at representations of that and take some subcategory of the representations and return. And again, we'll be able to draw pictures like this. And in this case, our object labels are always as trivial. Each of these things is a representation, and because of the co-product on UQOG, we can two sort of representations together. And also, since the diagrams that turn upside down. This. Finally, maybe the simplest example. We can just take the thing we started out talking about, which is temporally modulo some relation. And we have strands, these unlabeled strands. So in this case, we would have a single object and a single strand type. And then when it comes to define these vector spaces, it's just going to be all possible spaghetti pictures we can draw inside, all possible pictures we can draw on a disk. These unoriented unlabeled strands modulo some of those relations I was talking about at the very beginning. For example, this picture plus that picture minus square root of 2 of this picture plus that picture. That's all easy. And that gives you the sort of first non-classical example. So, if there's time, eventually, I guess my original idea was to sort of just talk about these things in much more detail and get more familiar with computing, but then I realized that it would take a very long time to get to the interesting theorems. So I kind of changed gears on that. But now I have the dilemma I've been talking about these things in the abstract, but it's nice to illustrate them with concrete examples. So, well, I think in the course, and I guess it would be next time, approving this will sort of carry the proof along, drawing pictures like this, and that will maybe give you a little more familiar with so, just pause here and see if there's questions.
So for each of these disk diagram disks or the circle, you've got a vector space.
Right. And
then what does this mean here? Given some diagram like this,
so in you can think of it as kind of like an operad action. That's the way it would be defined. I guess the other pedagogical mistake I was making here is I was trying to choose some language that was neutral between planar algebra language and two-category language and other things. But the way they would say it in planar algebra land is given a puncture disk with some strands connecting things. And so everything's labeled. We've got labels on the regions and labels on the things. And now we have vector spaces associated to each of these circles because they are a circle that's appropriately labeled. And then we want to map to the vector space associated to the outer circle. And I guess it should satisfy an operad substitute ability condition. But if we were describing it in a two-category way, we would really just say, given some picture in the disk here and another picture in an adjacent disk here, we just leave them together. And it turns out that's be thought of as a very special case of one of these operad diagrams where we sort of take the disk and have two gigantic holes in the middle and all our strands just kind of go like this. So it turns out that that's enough to reconstruct everything. So maybe it's best, if you're unfamiliar with these, just to think of the temporally new examples, which we did spend a little bit of time discussing. And then the only thing we might want to add is it has to do with like idempotent completion. I said template leaf has only a single strand type and a single region, but there's a sort of, it turns out to be convenient to have, if we have something labeled by an integer, say, k, but that's a shorthand for the sum of pictures with some coefficient c sub I times some diagram d sub I. We have k strands here. And what is this linear combination? It's just the thing to make this into a minimal idempotent. So we started out with a very small collection of strands. You know, if you have a category or an algebra and it's a category, it's a category, and you don't have enough, you know, there are minimal idempotents which don't correspond to objects. That's inconvenient, but it's always possible to add those objects in. And so that's in some sense what we're doing here. So
I was gonna ask, so in like the temporary leave example, we know what the field simulations are, like you have described them, but like what is the path integral?
for that.
Yeah.
And for what we're doing, if we think of temporally lead, so there's some ambiguity because it turns out that temporally lead uses a double Y because both the 2 category and the 3 category. If you think of it as a 2 category, which is what I've been drawing here,
Yeah.
the invariant is a derived zero. So
I mean, I don't know what that is.
okay, but that this, and what we'll do in the we're going to basically illustrate and prove this theorem in the case of the temporal lead category or things like it, and so we'll say very explicitly when we're going to prove what the derived invariant is. But if instead we're showing that we thought of temporal lead as sort of 3-dimensional pictures, meaning you can draw crossings and have them with these things embedded in a 3-ball rather than a 2-ball. And then we go through the thing, we'll get a disguised form of like Reshikiva 12 type invariants. Yeah, so maybe next time I'll start on proof of this, so that means this is a good time if we have any other questions about diagrams like this. Or there's a book by Kaufman and Lenz, so I just temporally lead that's pretty good. Yeah, there's lots of examples beyond temporal lead, but the techniques you use for this, generalizing, so it's actually one thing since we've got time. Let me mention one important thing about these examples. Yeah, let me just say 2 things. Okay, so we say X and Y that are in our region colors. I didn't say explicitly, but given this data, we can construct fields and relations. So the fields are the pictures that are labeled this, and the relations are just sort of setting a diagram like this equal to its evaluation. So once we have fields and relations, we can construct these 1 categories that we've been talking about. So in particular, we have 1 category associated to the standard interval with variables x and y and points. So this is 1 category. And we want to assume is semi-simple. And let I sub x, y be a set, completes complete set of minimal idempotents. So any semi-simple one category is isomorphic to a category of graded vector spaces. We're assuming here. So everyone know what a minimal idempotent is? Okay. Okay, so so an idempotent just means that E squared is equal to E. So think of it as a projection. And then there's a partial ordering of idempotents. So so we think this, if this was an endomorphism of the vector space, we would think of it as maybe some projection onto a subspace. And so the inclusions of subspaces give you a partial ordering of the idempotents. And minimal just means minimal with respect to that ordering, and bigger means the image is one-dimensional. So if we've got a matrix algebra, an example of a minimal idempotent would be a matrix which has a single one somewhere on the then we can also define, so what do I mean by a complete set of minimal idempotents? I don't mean every single possible minimal idempotents because there's infinitely many of them. I mean just a representative from each equivalence class. What are the equivalence classes? Well, we say that E is equivalent to F if there exists E of V such that UV is equal to E, VU is equal to F. So again, for finite dimensional algebras, that just means that they have the same, finite dimensional, for a matrix algebra, it just means they have the same dimension. But in, this definition makes sense in binomial algebras also, where it gets a little more interesting. And also note, everything I've said so far, I could replace algebra with linear one category, and it still makes sense. In particular, these idempotents would live in the endomorphism space of some object, and E and F might be in endomorphism spaces of different objects, but U and V still choose it. So that basically, we've got objects X and Y. Here's E going from here to here. F is a morphism from here to here, and I would have sort of U and V running back and forth between. I get a U and V. I get sort of goes the same. An example in temporal relief, we could take E to be the empty picture, and we could take F to be 1 over the loop value of this picture. So I'm thinking of these stacking vertically. So this is a morphism from the empty strand to the empty strand. This is a morphism from the strand with 2 points to 2 points. And then I can let U be this picture, the 1 over delta, that picture. So if I stack U on top of V, I get a loop. I get 1 over delta times the loop, but then the loop is delta, so that I stack them U on top of V, I get this picture. And if I turn it around, I completely get that picture. So these are two different idempotents in the temporal loop category. So the temporal loop morphism modules. And so in our complete set of minimal idempotents, we would just pick one of these. It doesn't matter which one. But and so the theorem is anytime you have a semi-simple one category, you can find everything. In some sense, everything is controlled by the set of minimal idempotents. If this were some kind of semester-long course, and we would have spent a couple of weeks at the beginning just working this out in detail for temporal relief, just give you some feel or intuition as these things work. And so one consequence of this is that if we have, suppose I have a strand and I'm giving some set of edge labels. And I consider the identity map of those strands. So just some arbitrary collection here, but that can always be written, let's say my outer region labels are X and Y. This can always be written as some over idempotence in these continuum set for vendors of x and y of pictures which look like this. Where I have E in the middle, and then I have my original labels there, and then I've got some kind of alpha, beta, some kind of, on these vertices, I'm always choosing something within these vector spaces. So in other words, any morphism is a sum of morphisms which factor through our particular set of middle line equations.
Does that have to do with the path integral also?
No, but this is something we would talk about even if we weren't. So you're wondering how do you prove this?
I'm just wondering if that equation is the same as the path integral equation for.
No. This is just a statement about, this is sort of elementary linear algebra. The fact that I said this set of idempotence is complete means that I can basically factor the identity morphism into morphism from this, this arbitrary object to E, and then another thing that goes back. And there's a sum of such things. And once we have that, so what I wanted to do is state the spine theorem, which is the main technical tool in doing calculations, and it's kind of obvious. Often it's not even stated as a theorem. Let's illustrate it first. So we'll have, again, working in this example of these two category type diagrams, we can consider a surface with some boundary condition. And what we want to try to do is find a basis of this vector space. Because in order to do this path integral thing, we're summing over orthogonal bases of a vector space like this. So for if we're going to do a calculation like this, we've got to be very good at finding bases for these vector spaces, testing whether they're orthogonal, and so on. So how do we do that here? Suppose my vector space is an annulus, and my boundary conditions say I have a single strand here, another strand here, and then I have sort of arbitrary stuff in the middle. And some arbitrary, actually let me correct, so it's two things here. So arbitrary diagrams that have this on the boundary. So given that boundary, a spine is just a topological notion. You can find, I have another color. I'm going to find inside one complex, and the curves I'm drawing here should not be confused with these labeled things. So pretend it's a different color. I'll draw it dotted. Okay, so what I've drawn is a sort of a graph inside the surface. And this graph has a property that if we take a neighborhood of the graph, so now I'm just drawing a thin neighborhood, it goes around the graph. So we've got this thin thing here, that basically the entire surface, modulo these boundary points, sort of the deformation retracts into that. And so the theorem is that this vector space has a basis of labelings. For any spine. So my spine is by definition a one complex that the surface retracts onto, and again this retraction leaves these little boundary points space, the spine S. This vector space has a basis of wavelengths of S. So what does that mean? Well, again, show this picture again. So before I was emphasizing that this dotted line, is not one of these curves that we're drawing up here. And now it is going to be one of those curves. I can consider diagrams of the form this, where we've got our fixed boundary labels A, B, and C here, and then we can have some other labels, E, F, and we have things like vector spaces for these vertices. And so we can choose a basis of vector spaces, labels of those spines where we might maybe I should say spanning set. No, it's so. Yeah, no, I want to say it's actually a basis that things are linearly independent. So the so what do I mean by all wavelengths? Well, for these guys here, these labels Y and our set of minimal idempotence. So and then the labels sort of for these vertices sort of run through an orthogonal basis of that vector space. Or just the basis. So how do you prove this? Well, first, any diagram clearly lives inside this new regular neighborhood because I've got this sort of deformation onto there. And then this thing I wrote down here about, so let's concentrate on this part of the picture. So we have, here's our neighborhood, we have some things coming in, and then arbitrary stuff happens in here. And actually, I guess we could have multiple strands running around. So the first thing to do is use this result to take the strands here and write them as sum of things which factor to a single minimal idempotent. This is just too sloppy. This is my close-up of some neighborhood of the spine. The first step is that everything lives inside the neighborhood of the spine, so that means I've got a picture which looks like some number of strands, and then arbitrary stuff happening there. I apply the limit up there to cut things, so every diagram looks like a sum of things, where we have only one. Instead of the arbitrary strands with arbitrary labels, we can cut it like this. And now if we look at the ball here, I have a ball with these three minimal idempotents on the boundary, and then some arbitrary pictures inside that we saw from that relation one.
No, that's okay. Take your time. We have an exam starting at 1, but
Okay.
Just
Okay.
take your time.
Okay. We had that evaluation map. So any diagram that looks like this can be replaced by one, which looks like this. We just put a big vertex in the middle. I just put it down before. So when we're left over, we have this. So that's the proof that pictures of this one span. And then when you can define an inner product, we'll do it next time to show that they're So, I apologize for my incorrect assumption that people were familiar with these sorts of pictures. Because they were like all the rage when I was in grad school, and then there's Warren Jones and his students that continued to work with him. So I was worried about spending too much time from my material as well.
I'm more comfortable with it in the planar algebra's language, where there's also these pictures, these string diagrams and categories. The vertices are just morphisms.
Right. So you were wondering how to.
So still practicing going back and forth between the two.
Okay, so there's.